Hello. Well, we're now going to begin the review questions at the end of Chapter 12 on optics. And these are on page 421, the review questions at the end of the Chapter 12, Geometric Optics. Okay, we're going to start right at the very top. Review question number 1. Suppose you want to see your entire body in a flat mirror. Do you need the mirror that is as tall as you or not? And hint, look at figure 12.1. Well, here, you remember, if this is the mirror, and you are standing, well, let's first get you standing here. Here's you standing right here. And here's a mirror. Okay, and you're looking straight across. Okay. We assume that light is coming from, is dispersed light, and light is coming from essentially all points in the room. This is the mirror. The light at your feet can come right here and bounce and hit your eye. And so from symmetry, we can see that this is the angle of incidence. Here's a ray of light. Here's the angle of reflection. And because of this, because these two angles are actually similar or equal, this distance here is equal to this distance here. And so actually, in general, the mirror only has to be essentially as tall as half your body. So that's all actually we only need that little segment. We only need the mirror to be from here to here. So actually it's half your body, or actually even maybe a little bit less than half of the body is all you need in terms of length of the mirror. Number 2, if you were doing a very precise opto experiment and you need a curved mirror that will sharply focus all horizontal light to a single point, which kind of mirror should you use? A parabolic mirror or spherical mirror? Well, the answer is parabolic mirror, and this is found back on page actually back at the beginning of the chapter where we talked about parabolic mirrors, and that's on page 390, where at 390 it says, anyway, it talks about these differences on page 390. Basically, parabolic mirrors will focus, it says back to the bottom of the parabolic mirrors, will focus the light actually to a mathematical point. But they're hard to make. Parabolic mirrors are hard to make. The other kind of mirrors, the spherical mirrors, are much easier to make, and they approximate, for small angle, for large radiuses, approximate the shape of a parabolic mirror. So that's the answer. Number 3, what is the difference between a virtual and a real image? Remember, a virtual image, like the one in the mirror, the image is formed where the rays of light, the virtual rays of light form. So here would be your body here. It's a virtual image. The image is formed, typically it's formed back behind the piece of glass, and it's formed by an extension of the light, of the rays of light, back behind the optical piece. Remember what I say is, if you have to break through the glass to get to the image, and that's a virtual image. The real image is formed where real rays of light focus down. Okay, and you can actually put a piece of paper here, and you'll see the image actually on the paper. Okay. Number 4, look how the pencil, this is the diagram here, look how the pencil looks disjointed above and below the water level in the picture on the right. What causes this? Okay, let's look at this. I'm going to draw this. Well, if you look at this figure, this is number 3. Here's a jar of water. And the pencil, here's the pencil, but here it looks disjointed, and it looks kind of like this. It looks kind of like that. Maybe that's a bad drawing. But this is water. Okay, now what forms that? Well, it's hard. Suppose your problem was to draw this in a way where you can see really what's going on. Well, it's hard to see it this way. But if we turn it and look on the top down, say we view it from the top, looking down, okay? What does it look like then? I'm going to, instead of drawing a glass, I'm going to draw the container just as a rectangle. This is water, and the front glass is right here. This is the front glass, and this is air. Okay, and we are looking from over here. Here's your eye. Here's your eye, and you are looking this way. Okay, the pencil, that is where the real pencil is. Okay, that's where the real pencil is in the water. Again, you're looking down at the image. Okay, but remember now, suppose that I'm going to draw a ray of light from your eye. Let's draw the image backwards, starting from the light. Suppose your eye is a laser. Let's think of it going backwards, and then we'll turn it around and go the other way. The ray of light, can a ray of light go from here, can the ray of light go directly to the pencil? No, it cannot, because there's an index of refraction, contrast. So what has to happen? If we want to shoot a laser beam from here to here, how do we do it? The ray has to come here. Remember, we draw the normal, and the Snell's law. Here's the angle of incidence, and the angle of reflection, the angle of refraction is right here. Angle of refraction. This index is water, 1.33. This index is air. Okay, so the light ray will be bent into the pencil. Okay. This is just a normal way of drawing a light ray, like you've done in some practice problems. Okay, well now we're going to flip it around and say, actually, the ray of light is traveling this way. The light source is behind the pencil. Okay, the rays of light come out at all angles, but the only one that hits your eye is the one that travels at this angle, and then it refracts outward, and it comes here into where your eye sees it. Okay, so this is just Snell's law. The ray of light comes from the water, where the index refraction is 1.33, and then it bends outward because of Snell's law. Okay, so that the ray of light actually bends like that. But what do you see? You think it's over here. And you think it's over there because when you don't have if this were just air, and here's your eye, I'm going to draw the same thing, just displaced. If this is air right here, like it is above, see here, it's just air. Above here, the light just travels straight. Okay, when you're up here, the light just travels straight, and so the light ray is unbent. But when it's in the water, the light ray is bent, and so you want to join this and this together. You join where they come together here. It's continuous, and and the bending of the bending of light here makes it seem like it's not coming from here, but it's actually coming from here. So I hope that explains it. Okay, number 5. These are tough questions. Some of these are hard questions. Explain why you can see through a window. Explain why you can see through a window, but you can often see your reflection in the window as well. Okay, that goes back to the lecture where we talked about reflection and refraction happen at the same time. Okay, here's a window. Okay, if here's a laser beam, we get a reflection here. I'm going to draw the glass is really thick. We get a reflection. This is a reflection. But we also get a refraction. And then the light ray comes through here. The ray is refracted, and then it bends back out. Okay, so this is the refracted ray. Refracted. Remember, percentage-wise, this ray here is about 96% of the energy, and this one is about 4%. And it really depends on the polarization of the light ray, which we haven't really talked about yet. But so this explains why when you look through a piece of glass, you do see a reflection, but it's a very weak reflection, only about 4%. Okay, number 6. In my church, there is a special window between the foyer and the nursery that allows parents to look into the nursery to check the little children. However, so you can look into it to check the children. However, from the inside of the nursery, the window looks like a mirror and the children cannot see out of it. That way, the children cannot see the parents when the parents are checking on them. Okay, essentially the question is, how does this work? But it goes on. Consider a light ray. It gives you a hint of maybe how this might work. Consider a light ray striking the window from the inside of the nursery. Will it be absorbed, reflected, or refracted, or some combination of these three processes when it hits the window? Also consider a light ray striking the window from the outside of the nursery. Will it be absorbed, reflected, refracted, or some combination? Well, it's actually a combination. It's actually a combination of effects. Okay. This whole idea of being able to see through a window is kind of a one-way window. It's really just an extension of this whole concept. But I'm going to redraw it. Okay. Make sure we're recording. Yes. Okay. The idea is, here's your window. Okay, you have two rooms. Okay, this is the nursery, and this is a hallway. Okay. Now, the nursery, let's suppose the nursery is very bright. Okay, the nursery is bright. There's a lot of light in here, but the hallway is is a little bit dark. It's a little dark. Okay. Okay. So this is kind of like the idea if you have a window, and you have a window, and it's dark, and you're, for instance, okay, here, for instance, this could be like a dark outside, or say this is a dark outside. Okay, and this is inside a house. This is really kind of the same. This is really the same thinking. Okay. If you have a bright light here, okay, what happens? The light rays come through here. Light rays come out. Remember, 96% will be. Let's look at the large window. Okay, we're going to get reflection and refraction. And here's the 4% that's reflected, and here's a 96% that's refracted. And this refracted ray, again, it will actually, there'll be a 4% reflection here, but again, the majority of this will come right through. And so if you're standing over here and you see a bright light, basically the contrast is what we're interested in. It's dark over here. Most of the light that's transmitted to the window is going to come through it. Because you're in the dark over here, relative to dark hallway, you're going to be able to see the bright lights in the nursery over here. And so if there's a person over here, when his light rays, reflected light rays, hit the window, the majority of that energy will transmit through it, and because of the contrast, if a person standing over here, you'll be able to very clearly see what's on the other side because of the bright lights. Okay? Now consider the other way. Okay, same setup, bright nursery, relatively dark hallway. Okay. The lights from here, don't allow a lot of the light. Whoops. Okay. Here's you, the parent, standing out here. Now the light is the exact same thing happens. Okay, the exact same thing happens. But the light energy here is low. Okay, so even when 96% of it comes in 96%, when you have a baby sitting here, okay, this energy still gets to, it's the light, the light ray from the parent still gets to the child, but it's low intensity, very low intensity, because it's so dark outside. Okay, it's so, and in contrast to the very bright energy over here, the contrast is actually hard to see. Okay, so, and in fact, he would have a much easier time. In fact, this energy from the parent, I'm going to say energy of the parent, is actually smaller than his own reflection. His own reflection, which is 4%, is much higher in energy than the parent energy, simply because it's dark on this side. Okay, so that's the whole idea. It's really a similar effect. It's if your windows are open, excuse me, you have a window and it's dark outside, but it's bright inside. If a person came and stood right at the dark window, you would have a very hard time seeing him, okay, because of the contrast of light intensities. So that's a kind of a neat concept, isn't it? Okay. Number 7. The index of refraction of substance A, the index of refraction of A is 75% of that of substance B. the index of refraction of A is 75% times that of B. Okay, that's index of refraction. In which substance will light travel the greatest speed? Okay, well remember, the velocity in a glass or a material is the speed of light divided by the index of refraction. Okay, so we have the speed of light, speed of light of A equals C divided by NA. Speed of light B is C divided by NB. Okay, so NA is smaller than NB. Okay, so if NA is smaller, that's going to make this velocity higher. This number is larger than that, so that's going to make this number lower. Okay, so when you have a smaller index of refraction, now remember, the index of refraction, the smallest it can be is 1. So it's kind of like we're comparing 1 to 1.3. Maybe this is NA and this is NB. Okay, NB. So the speed of light is slower when the index of refraction goes up, the speed of light goes down. In other words, another way to think about it is the speed of light in a glass is slower. It slows it down than, say, in air. Okay. Number 8. Given the statement above, in which substance A or B will the substance most likely have the higher density? The higher density is the one where the speed of light travels is slower. So that would be substance B. Okay. Number 9. When a photographer is taking a picture and does not use autofocus, she manually turns the lens around. She manually turns the lens around turns the cylinder around the lens. This focuses the image onto the film. What is a photographer doing to the lens when you spin that cylinder? Basically, you have here's your camera box. Here's the film. And when you rotate, you're moving the lens back and forth. You're moving the lens back and forth, and you're adjusting where that focal point hits the film. So you're moving the lens, if that's the lens, you're moving it a little bit back and forth like that. Okay, number 10. How does the human eye keep the image of the object when it is viewing focus at the same place, even when the object is moving? Well, it's very similar to this. Basically, the shape of the eye actually deforms. This is back on page, well, in the past part of the chapter. I hope you read it. We didn't really even talk about it, but you're actually changing the whole. They talked about on the page 411. The whole. You're not really moving the lens back and forth, but you're changing the shape of the front eyeball. So you're actually changing the shape of your front lens is what you're doing. And that actually has the same effect. Okay, at this point we're going to flip over to page 422 and we're going to start the practice problems. Okay, practice problems on page 422. Okay, and this is number 1. Okay. The object is placed 3.5 centimeters from a concave spherical mirror whose radius is 5 centimeters. Okay, so it's a concave and it's 5 centimeters and you're 3.5 away. We'll draw it like this. The first thing you do is to draw the optical axis. The optic axis. Okay, here's your concave mirror, and it has a radius of curvature of r of 5. This is r, that's 5, and so right in the midway between here and here, if that's the radius, then that would be the focus, or the focal point, remember? Because the focal point is 1/2 of the radius, okay? And the object is placed 3.5 centimeters away. So 3.5. 1, 2, 3, 1, 2, 3, 5, right here. And there's the object. Okay, so now you remember how we're going to draw 3 rays. Okay, the first one is parallel in. Okay, parallel in. It comes parallel in, and it goes. If you go parallel in, it comes through the focal point. Goes through the focal point out. Okay, so that's number 1. That's ray number 1. Okay. Now, number 2 is, okay, through the focal point and parallel out. Okay, so we come through the focal point. This one we start at the top and we'll go through the focal point and then parallel out. That looks about parallel. That's number 2. Okay. Right? Now the third one is through the radius. Okay. So now how do we get to the radius? We get to the radius by taking it way, hang on for a second. Whoops. You know what? I really should have drawn this further out, or maybe a little bit smaller, because I'm going to have a heck of a problem. I'm going to have to redraw this. I apologize. I'm going to redraw this and expand it. My angles are too big. Sorry about that. Okay, and I'm going to draw this as a slight concave mirror. Whoops, not a very good drawing, but essentially that's a concave mirror facing this way. Okay, here's my radius. I'm going to expand the scale. There's my radius. Here's my focal point, 3.5. And I'm going to draw it a little bit smaller. Okay, so I've now just expanded my scale. Okay, okay, ray number 1 is parallel in. And out through the focal point. Okay, there's number one. Okay, that's number one, parallel in, out through the focal point. Number two, through the focal point and parallel out. Number two, through the focal point and parallel out. Okay. Okay, and number three is through the radius. Here's the radius. Number three is through the radius. Okay, so here's through the radius. Goes like this. It goes through the radius, and then it bounces back right on itself. Okay, it goes through the radius, and then it comes right back on itself right there. So, okay, so where do all these meet? If I drew it right, they're meeting right over here. I'm going to say I drew it a little bit wrong, essentially right here. Okay, here's the